Hey, hello! Welcome to day 1 of your HSC chemistry video series. I hope this video finds you well, and I'm sure that by the end of this you will learn heaps about chemistry. But before we get started with all that fun sciencey stuff, yes, fun sciencey stuff, I just want to make a note that I'll try to make this video series as detailed as possible, such that it includes most of the notes that's written on the website. If you have not checked out the notes, I highly suggest you to. But if you have not, that's fine as well, because the main reason why I decided to make this video series to help students who are more visual and audio learners, right? So this would serve the purpose, and yeah, I'll try to make it as detailed as possible, and I'll try to make it as concise as possible. This is a pretty laid back sort of chemistry conversation teaching kind of style. So yeah. So let's just get started. So module 5, I'm not sure if your school have started module 5 yet, because from what I've seen, school starts from different topics. So some schools starts from topic 8, so module 8, 7, and some do 6. So, but most schools do module 5 first, so that's fine. So I'll just start off with module 5 because I feel like this is probably like the most appropriate way to do it, in the sense that content of module 5 flows really nicely into module 6. Anyways, module 5 is called equilibrium and acid reactions. Just in case you haven't done module 5, there you go, that's the name of the topic. And in this topic we'll be dealing with equilibrium reactions and also some theory behind acid reactions as well. So like most other topics, there are many sections, right? So the first section of module 5 deals with, so the first one is static and dynamic equilibrium. So this is the first topic within module 5, so to speak, and under each section there is a inquiry question. So we'll be starting the first topic, which is static and dynamic equilibrium, and the inquiry question that we will be discussing for the first section is: what happens when chemical reactions do not proceed to not equilibrium, sorry, does not proceed to completion. Yeah, so what happens when chemical reactions do not proceed to completion? So basically there are two types of reactions, right? The first type of reaction is, oops, don't know why it didn't change color. The first type of reaction is reversible reactions. And the second type of reaction is non-reversible reactions or irreversible reactions. Right? So an example of a reversible reaction would be the Haber process, which is nitrogen gas reacting with hydrogen gas, giving you ammonia. And I'll explain why this is a reversible reaction soon. And a non-reversible reaction could be magnesium metal reacting with oxygen in the air, giving us magnesium oxide. which is a white powder, and you usually see like a glow, like a bright glow. I think your teacher should have done this experiment at school. back in year 11, or now in, we call it year 12, like when you do module 5. So why is this a reversible reaction, the Haber process? Well, if you have a look, we have a double arrow here. So what this signifies is that nitrogen gas will react with hydrogen gas to form ammonia, and ammonia molecules will react with each other and to form hydrogen gas and nitrogen gas. Therefore, the reaction has two ways, right? The forward reaction and a reverse reaction. So in the reverse reaction, the products would reform the reactants. If we have a look at non-reversible reactions, such as the magnesium metal reacting with oxygen in the atmosphere, forming magnesium oxide, there's a forward reaction, but there's no reverse reaction because magnesium oxide does not then decompose back into magnesium and oxygen gas. And we'll explain why this is the case in the next video. But for now, just understand that non-reversible reaction means that it's only one directional, whereas reversible reactions are two directional, right? There's forward and reverse reactions. So sweet. So now we have sort of answered the inquiry question in a sense, but not quite. But so you say, what happened when chemical reactions do not proceed to completion? Well, reversible reactions happen, right? Because some of the products are then consumed to form reactants. So at the end, there is no complete reaction in the sense that there are reactants and products present. Whereas in non-reversible reactions, aka complete reactions, all the reactants are consumed, or like one or more reactants are consumed, and products are present, and these products do not reform the reactants. Okay, so under each inquiry question there are learning objectives, and in this video we'll examine the learning objective pertaining the following. Okay, so this is one of the learning objectives that is under this week's inquiry question, or this section's the first section's inquiry question, and we already explored the inquiry question was about what happens when chemical reactions do not proceed to completion. And now this is learning objective 1, and it helps answer the inquiry question. There are many more which we're going to explore in the upcoming videos, but in this video we will only be focusing on this learning objective. So let's just break this down, right? So right off the bat I can see that there are at least 2 sections, so just because of the word "and". So if I can break this up into the relevant sections like this, it might make it easier. Then I'll probably underline the keywords. So model static and dynamic equilibrium. So in order for us to do that, we need to understand what equilibrium is actually. So and also what static equilibrium is and what dynamic equilibrium is. The second section is to analyze the difference between open and closed systems. What I'm going to do here is that I'm going to first talk about open and closed systems first, and then we'll look into static and dynamic equilibrium after, because it will make our lives easier in terms of understanding these concepts. Alright, so yeah, we'll look into open and closed systems for now. First. So, open systems and closed systems. So first of all, what is a system? So a system is basically So a system is basically a chemical environment in which a chemical reaction takes place. So if we have an open system, it essentially means that the chemical reaction is taking place in an open environment. Vice versa, if we have a closed system, that means we have a chemical reaction that is taking place in a closed environment. So what's the big deal about having a open environment versus a closed environment in which a chemical reaction takes place? Non-reversible and reversible reactions can occur in open and closed systems, right? But there are some differences that you can use in HSC chemistry, which we'll talk about later. Let's just have a look at this generic reaction. Just say we have A gas plus reacting with B gas to form C gas, okay? And let's just suppose that this reaction takes place in a open system for now, okay? So let's just say it occurs inside a open container like this. So here's the lid, and then let's put in our materials inside. So we have A gas, B gas, as well as C gas. Okay, so there are many of each, A, B, and C. I'm just going to draw one of each. And then outside our open system, right? This is our open system, our vessel. There will be other substances, right? So there will be other chemicals involved. So since we're on planet Earth, there will be oxygen gas. What else? There will be argon gas. Oops. There will be argon gas. There would be nitrogen gas. Right, and many more. Okay, so and there will be probably some pollutants as well, right? So carbon dioxide, etc. So what happens is that these gases which surround the system would actually get in. Why? Because it's an open system, right? So in our case, it's an open system, and then we'll have a look at closed system after this. They can all basically move into our environment, our system, right? Our open system. So what happens is that some of them might react with A gas, and some of them might react with B gas, and some of them might react with C gas. So it would disturb our chemical reaction, and this has an implication, which we will see later on in the upcoming weeks, when we learn about Le Chatelier's principle and collision theory and all the others. Let's have a look at the example of a closed system. So we have a closed system here. right? And let's say we have A gas, B gas, and C gas. This is just like, you know, the thing that you use to open the lid, I guess, but it the whole thing is closed, okay? So same thing, we'll have some chemicals in our environment, in the atmosphere, okay? Like this would vary depending on what environment our vessel or our system is what do you call it, located. So what happens is that since this vessel is closed, these gases cannot enter the vessel, right? They cannot enter. So if I use a different color, they cannot enter, right? So what happens is that all the reaction that's taking place inside this closed environment are due to A gas, B gas, and C gas, whereas the reaction that is occurring inside this open system could be between all of these gases, right? We don't know what exactly A, B, and C are, so we're not sure, but you know, they could all potentially be involved in the reaction. It's not just A, B, and C, you know. Oxygen gas can react with A, maybe, depending on what A is. Carbon dioxide could react with C, you know, etc. So from here, what can we say? So open systems involve the interaction between matter in the system and matter in the external environment, right? Involves okay, now let's have a look at closed systems. So closed system does not involve the interaction of matter in the system and matter in the external environment. This should be matter. So this should be open systems involve interaction of matter in system and also matter in the external environment, whereas closed system does not involve interaction of the matter in this system or closed system and matter in the external environment. Alright, so there's one last thing. The thing that I'm going to talk about is energy. Just say that this container has a temperature of 400 degrees Celsius, right? Or enthalpy, if you like, internal energy of 400 degrees Celsius. And outside, so the external environment that's surrounding this container has a temperature of maybe 100 degrees Celsius. So it's pretty hot. So what happened is that heat from the container would leave like heat produced in the reaction would leave the vessel by radiation, right? Heat will be radiating from the vessel into the environment that is cooler, right? So this is like thermodynamics, where heat moves from a hot place, like a hotter environment, into a colder environment, right? So as a result, the vessel would, or the system would lose energy into its environment, right? How about in closed system? It's same thing, right? There will still be an interaction of heat between the internal environment and external environment. So this could be like a milk bottle, for example. You take your closed milk bottle out of your fridge. There's milk inside. You put it on a table, and then you give it some time. 1 hour has passed. You come back. The heat, the temperature of the bottle, of the milk bottle, would be hotter than when you initially took it out of the fridge, because it has gained some energy. Would you agree? So maybe when you took out of the fridge, it was 10 degrees Celsius. Outside is 100 degrees Celsius. Heat will move into the milk bottle from the outside environment. So in either case, there will be an exchange of energy between the system and the external environment. So let's just write that down. So that's a similarity between open and closed systems, right? Both So both open and closed systems involve the interaction or exchange of heat energy with the external environment. The system may lose energy, or they may gain energy to or from the external environment, right? Does not matter. So open can acquire or lose heat. Closed systems can acquire or lose heat depending on the external environment. Yeah, so now let's just go back and see where we're at. So now we have analyzed the difference between open and closed systems involving reactions that could take place in an open environment or closed environment, both reversible and non-reversible. And now it's time to see the differences between static and dynamic equilibrium. Okay, so let's just do that. Okay, so before we get started, let's I'll give you like 3 seconds to think about this. If you need 3 seconds, what is the common word between the two? Okay, 3 seconds up. I hope you saw the common word. It's equilibrium. Okay, so in order to understand static equilibrium and dynamic equilibrium, we need to understand what equilibrium is, okay? So equilibrium is a state of the system in which the forward rate of reaction is equal to the reverse rate of reaction. So let's write that down. Alright, so let's have a look at an example of when equilibrium is established. Let's just take this, let's just take a generic reaction. Okay, A gas reacting with B gas, producing C gas, and C gas will react with each other. C plus C gives you A plus B. Okay, let me just draw out a table for us to understand this easily. But let's just say initially we add in A gas and B gas, okay, at time equals 0. So I'm going to label the axis here. Here's time. Let's say this is in minutes. And this is in concentration. Right, and units of concentration is moles per liter, or capital M. And let's just say that so what happened is that we have A gas and B gas. So let's just draw that in. Just say this is A gas. Oops, oh no, that's not concentration. And we have B gas. Let's just say you have more A than B when we initially put in, doesn't not really matter in our example here. What happens is that A gas will react with B gas to form C gas, okay? So over time, as time progresses, we have more C gas, right? So the moles would increase and therefore concentration will increase, right? So C equals to N over V. As mole increase, concentration will increase. So, like assuming our volume stays constant, which is what we're assuming here. Let me just draw this. Let's say it happens like, just say concentration changes like that over time. For C gas, this is C gas. And then we will have B gas. Like that, and we also have A gas, which is, let's say, it's like that, okay, like that. All right, so I can say from this graph, what color should I use? This. I can say from this graph, equilibrium is like around here. Oops, that's a bad line. Equilibrium is like around here. The reason why I say equilibrium of the system of this reaction is around here is because it is at this point where all three gases, or all the species in the system or reaction, has constant concentration. So let me just label these species. I think I said this was B and this was A. And let's just assign some random values, concentration values here. Let's just say at this point, it is like, I don't know, 9. And then at this point, it's like 7. And like at this point, it will probably be like 4, okay? So when equilibrium has been established, and I'll explain further in terms of concentration what equilibrium means, the concentration of A equals to 9 moles per liter. The square brackets means concentration. The concentration of C is around 7 moles per liter, and the concentration of B is around 4 moles per liter. Okay, so at equilibrium, what we want to know, like what the point that I want to get across is that at equilibrium, the concentration of each species is constant. Okay, so like as shown here. Now, why are they constant? The answer lies here. This equilibrium is the state of the system in which the forward rate of reaction is equal to the reverse rate of reaction. That clue, or like the answer why the concentration of each species involved in reaction is constant at equilibrium. Notice that before equilibrium has been reached, the concentration of each species are not constant in the sense that they don't have a fixed Y value or concentration, right? The concentration, like take C for example, C gas, its concentration fluctuates. It increases over time until equilibrium has been reached. So maybe this is T equals to 5 minutes, right? Before T was 5 minutes, like T equals 1, 2, 3, 4, 4.9, its concentration changes over time. But when from T equals to 5 onwards, including T equals to 5, the concentration of C, A, and B are constant, are fixed at a certain concentration. So to do this, we're going to explore what is happening at a microscopic level, okay? So A gas plus B gas giving us C gas, okay? So when A gas reacts to B gas to produce C gas, it has... So when A gas reacts to B gas, for every 1 mole of A gas that is consumed, 1 mole of B gas is also consumed. And how much C gas is consumed? Well, it will be 1 mole, right? Because of mole ratio. Same thing, at equilibrium, we set the rate of the forward reaction and the rate of the reverse reaction is the same. So when 1 mole of C gas is produced, 1 mole of C gas is also consumed. So at equilibrium, 1 mole of C gas is consumed to produce 1 mole of B gas and 1 mole of A gas. So this happens at the same time. So scenario 1 and 2 happens at the same time. So what happens is that, what's the change in the moles of C? What do you think? It'll be plus and minus 1. Oops. Not sure why the color didn't change. Plus and minus 1 mole. And how about B? It will be plus and minus 1 mole. How about A? Plus and minus 1 mole. Since we said that the volume is constant, these are basically concentration values. Plus and minus 1 moles per liter, plus and 1 minus 1 moles per liter, and plus and minus 1 moles per liter, right? So what happens is that despite at a macroscopic level, the concentration of A, C, and B are fixed, right? So when you measure the concentration of A, C, and B at equilibrium, they would be fixed in concentration. However, at a microscopic level, A, B, and C are actually changing in concentration, right? They plus 1 mole, minus 1 mole, plus 1 mole, minus 1 mole, alright? At equilibrium. So the rate of reaction is not 0. That's the point, right? 1 mole of A is reacting with 1 mole of B to produce 1 mole of C, and therefore the rate of the forward reaction is not 0. Is the rate of the reverse reaction 0? No, because 1 mole of C is being consumed to form 1 mole of A and 1 mole B at equilibrium, right? So the rate of the reverse reaction is also not 0. So this is called a dynamic equilibrium. So this is a specific type of equilibrium. It's called dynamic equilibrium. That was an example of dynamic equilibrium. Forward rate, the forward rate of reaction is not 0. Reverse rate of reaction is not 0. However, let's assign some values to this. Let's say this is 2 and this is 2, right? It has to be greater than 0, right? Because this reaction occurring in a microscopic level. So 2 equals 2. They're equal. So if we go back to our original case, equilibrium is the state at which the system in which the forward rate of reaction is equal to the reverse rate of reaction. It's equal. Okay? So we look at this. We just randomly assign some number to say it's 2, or it could be 3 and 3, right? At dynamic equilibrium, when the system has established dynamic equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction, and the rate of the forward reaction is not 0, and the rate of the reverse reaction is not 0. And one last thing is that the change in the species concentration involved at equilibrium is constant. So we saw it here. The change in the species concentration at equilibrium is constant, right? A is at 9 moles per liter, C is at 7 moles per liter, B is at 4 moles per liter. These are the concentration you expect to see when you measure the system. Now, lastly, we're going to touch on static equilibrium. So, like equilibrium can be classified into 2 types: static and dynamic. We already touched on what dynamic equilibrium, right? The thing about static equilibrium is that same thing, it's a type of equilibrium, therefore the rate of the forward reaction is equal to the rate of the reverse reaction, right? So same thing, the rate of the forward reaction is equal to the rate of reverse reaction. And the same thing, the change in the species concentration at equilibrium is constant. So for static, the change in the species concentration at equilibrium is constant for the same reason. But we got to look into one example of static equilibrium now. So what is an example of a static equilibrium? Let's have a look at this. Let's just erase this. So it's graphite plus not plus to diamond. Oops. So graphite to diamond, okay? That's an example of a static equilibrium. Why? Or an example of a system or a reaction at static equilibrium. The reason is because graphite can be converted into diamond at extremely high pressures. Alright, you need high pressure to convert graphite into diamond, and that's the Ford reaction if it's written in this way. And the reverse reaction will be diamond being converted into graphite, and that would require high temperature. Okay, but but this system or reaction is at static equilibrium at room temperature, which is around 25 degrees Celsius, is a static equilibrium. The reason why is because the pressure at standard conditions is around 1 atmosphere, and this will be 25 degrees Celsius. So it won't be high pressure and it won't be high temperature, right? So these will be classified as extreme conditions, but under normal conditions or daily life conditions, the rate at which graphite or carbon atoms being converted into diamond, which is also carbon atoms, is almost negligible. It's so small, and the rate of reaction is so slow that we say that the Ford rate of reaction in which graphite is being converted into diamond is basically 0, right? So the rate of the Ford reaction is 0, and the rate of the reverse reaction, graphite being converted into diamond, is also 0. Notice that 0 equals 0, which means it still makes sense in equilibrium terms, where the rate of the Ford reaction equals to the rate of the reverse reaction, so 0 equals 0, and the change in the concentration of species at equilibrium, at static equilibrium, the change in the concentration of graphite is constant, is 0, alright, plus or minus 0, and the change in the concentration of diamond is also plus or minus 0, right, approximately. So that's that. So the difference between static and dynamic is the sense that the rate of the Ford reaction is 0 for static but greater than 0 for dynamic, and the rate of the reverse reaction is also 0 for static, but the rate of the reverse reaction for dynamic is greater than 0. So last thing, I'm just going to summarize that. So the rate of the Ford reaction equals to 0 for static, or the reverse reaction is also 0 for static, and then 0 equals 0, so the rate of the Ford equals to rate of the reverse. So this is static equilibrium, like when a chemical reaction or a system has reached static equilibrium, this is what happens, and the change in the concentration of species are also constant. And for dynamic, the rate of the Ford reaction is greater than 0, and the rate of the reverse reaction, is also greater than 0. So let's just say that's 2, and that's 2. 2 equals to 2. The rate of the Ford reaction equals to the rate of the reverse reaction. Okay, and the change in the concentration of the species involved in the equilibrium is constant for static, also for dynamic. The change in the concentration of species involved in reaction at equilibrium equals to 0. So we said that we already had a look at that before equilibrium has been reached, the change in the concentration of the species involved in the equilibrium reaction is not constant, right? It's not constant. It's constantly changing over time. So an example of dynamic could be the Haber process. So this one, when this has reached equilibrium, this reaction, this reversible reaction, then it is called dynamic equilibrium. Also, one last thing, so let me just get down to where we were at. Static equilibrium generally occurs in closed environments. So, closed systems. And they can also occur in open systems. So now, and for dynamic, equilibrium, they generally occur, for HSC purposes, they generally occur in closed systems. Okay, they could occur in open systems like deep under the Earth's crust and stuff like that, where the temperature is really high and the pressure is really high, and then some weird reactions occur. Okay, and the reason why dynamic equilibrium, like reactions that proceed to dynamic equilibrium, often only occurs in closed system, is something that we're going to touch on in later weeks when we explore Lichatti's principle. That's when we can really get a good insight into why. So for now, just understand what closed systems are, what open systems are, what static equilibrium is, what dynamic equilibrium is, what a system is, what does the term equilibrium means, and reversible reactions and irreversible reactions. So if you got that all down, then congratulations. If not, you can just check out the notes on the website where basically it covers all this in greater detail. And so yeah, see you next video. Bye.